Let's look at a complete walkthrough of free response question number 2 from the released 2012 AP Calculus AB exam. Now, this is a calculator active problem, so make sure you have your calculator handy so you can follow along. This problem is all about figuring out areas and volumes using definite integrals. So we setting those up conceptually, and then also using our calculator to find explicit numerical approximations. So let's dive in. Throughout this problem, we're going to be looking at this region R that is defined to be lying between the x-axis, our graph of log x, and our linear graph y equals 5 minus x. In part A, we're simply asked to calculate the area of R. Let's see how we're going to do that. So there are a couple of ways to approach this problem. There are two, and I'm going to show you both because depending on your preferences, you might like one more than the other. And depending on how you set it up, you're actually going to have more or less work to do in part C of this problem. So that's why it's in our interest to see both of them right now. So we have an area here that is between a graph and the x-axis. So one thing that we could do is we could approximate that area using our thin rectangles of a Riemann sum. And then what happens is the curve that my area is lying below changes, right? Initially, it's that blue y equals ln x graph. And then all of a sudden I move over to the side and the area that I'm looking at is lying beneath my linear graph, okay? So if I want to do a dx integral to calculate this area, using these vertical rectangles, I'm going to have to use the two different rules, okay? So if I set this up, that first left-hand region is going to be the integral from 1 here up to some x value that I'm not sure about right now. Okay, that's going to come from this intersection point right there. But I know that I'm going to take the integral of that curve, ln of x dx. That gives me the portion of my area coming from my blue thin rectangles. And then I'm going to add on the rest of the area. So I'm taking an integral from that mystery x value that I haven't found yet. And then if I work with that linear function, you'll see the x-intercept is happening at x equals 5. So I'm integrating the rule y equals 5 minus x dx. And that is giving me the purple right-hand skinny rectangle area. Okay, well, if I knew that mystery number given to me by that intersection point, I would be able to know the number that goes in that limit, type that into my calculator, and get my answer. So one of the calculator skills that we need to have is finding an intersection point of two curves. So let's pull up our calculator. Okay, I'll clear this out. So I have already typed in here my two functions. I've got y1 equals ln of x and y2 equals 5 minus x. So if I go to my graph, I hit graph, and I see I have those graphs plotted. And now I want to find that intersection point. So you can see I've already got that pulled up, but I want to show you how I did that. Okay. So what we need to do is hit second trace. Okay, that's pulling up our calc menu. And I want to hit option 5 because that is an intersection point. So if I do that, I need to give my calculator some help because it's not terribly smart, it turns out. So I need to use the arrow keys to go somewhere to the left of the intersection point I'm interested in. Hit enter. Then it's asking for a right bound. I need to go somewhere to the right of the intersection point and hit enter. You might then have to give it a guess, okay? And at that point, you want to move your cursor roughly over the intersection point. Here, we didn't have to. And you can see I now have x equals 3.69 ... and y equals 1.3 dot 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 as my intersection point. Okay. So if I record this over here, my intersection point star is happening at 3.69344 roughly, and the y coordinate is 1.30656. Okay, cool. Now I want to, the x coordinate here is this 3.69, right? That is the x coordinate where my rule changes from the log rule to the linear rule. So I need to insert that number as my upper limit here and my lower limit down here. Okay. So I don't really want to be doing a lot of typing there in my calculator. So I want to remind you that we can store that value in a different variable and use that in my integral calculation. Let me show you what I mean. So if I quit out here, the good news is the calculator remembers right now what x is. If I hit x, it gives me that 3.69344, that x value of that intersection point. So all I'm going to do is say x, and then I'm going to hit the store button, which gives me that little arrow. And then I'm going to store this in a different letter. I'm going to store it in A. Okay. So now if I call A on the calculator, it's just going to give me that value back. Hooray. If I was working with that y value, I would say, okay, let's pull up y. I'm going to store that. Let's say I store that in B. Okay. Again, I'm storing that value. Because if I jump back to my work for a second, okay, this is now what I'm calling A. That's what I'm calling B. So I know that all I need to do is put this A value in those boxes there, and that will give me the correct value here for this area. So how do I do this on my calculator? Well, we're going to hit the math menu because we're going to do some math. And remember, it's option number 9. It's function integral. So I have this first integral here. Let's input it as the integral from 1 up to my value that I've stored, A. Okay, you could just type in 3.69344 there, but that has the opportunity for us to make a mistake. Let's just make the calculator do that work for us. And then I want ln of x dx. Okay, that's my first integral. Now I want to add on my second integral. So again, I'm going to hit math, then 9. And now my variable, my limits are a up to 5 of, in this case, the function rule is 5 minus x. So if I hit enter here, this is my value. I'm going to get 2.986 rounding. That is the area of the region R. Great. How are the points divvied up here? Well, we get 1 point for the integrands. Okay. We get 1 point for the correct limits, both there and also these ones. And then we get 1 point for our correct answer. Now, what I want to point out before we move on is there was a second way to calculate this problem. So let me clear away my calculator for a second. Okay, because instead of using those vertical rectangles, I could have used horizontal rectangles. Okay, so let's start with the same diagram, but instead of interpreting the area, that way, let's have a slightly different interpretation. So I could use horizontal rectangles to approximate this area. Now, when I do that, remember that means I'll be using a dy integral. But the reason that you might want to do this is at a particular generic y value on the y-axis, I now don't need to worry about splitting my function in two because I can figure out, okay, I have, oops, this distance here all the way over to the pink linear curve. Oops. Grit. And then I have this distance here to the log curve. So if I can figure out those distances, I can just take their difference, right, to figure out the length of my skinny rectangle. Okay. Well, if this rule was y equals 5 minus x, or y as a function of x, I can rearrange that to write that x is, whoops, x is just 5 minus y. I can do similarly with the other curve. So if that rule was y equals ln of x, let's just hit that with an exponential function because that tells me that x is going to be e to the y. So in particular, this e to the y, that is the length of that yellow segment. And this 5 minus y, that is the length of this long turquoise segment. So if I wanted to set this up as a different integral, I could write this as, this time, my integral from, well, where do my rectangles start? They start at y equals 0, and they keep going up to my intersection point. So my integrals will start y at 0, going up to b, what I was calling b, the y coordinate of that intersection point. And now I'm just going to do 5 minus y, the longer length, subtract the shorter length, which was e to the y dy. Now, just to convince you that this is indeed giving us the same answer, let's try typing this into our calculator. So I'll hit math 9 to get up an integral. My limits are 0 up to, in this case, alpha b, where I stored the y coordinate. And now, okay, on my calculator, my variables are automatically x. That's no problem. I'll just do 5 minus the variable minus e to the variable. Let's see what we end up with. You can see it's exactly the same value, 2.986, and so on. So value in both ways. This way was a little simpler. There was just one integral, but you maybe had to do a little bit more work to set up that integral in the first place. Okay, part B asks us to build a volume out of this region R. Okay, region R is supposed to be the base of this solid. And if I take cross sections perpendicular to the x-axis, I'm supposed to get squares. Okay, it wants us to, without necessarily fully visualizing this solid or working out the answer, just write down an expression for this volume, okay, using integrals. Okay. Now, as I say, you don't have to fully visualize this. You shouldn't waste time doing that on the exam. We'll talk about how to actually get into this problem quickly in just a moment. But I want to give you some way of visualizing this. Okay. I can't fully visualize it. I can get close if I close my eyes, but it doesn't really matter because mathematically we can still understand the object. That is part of the beauty of math. So each time I take a slice along perpendicular to the x-axis, I'm supposed to get a square. Okay, imagine this is some weird looking cake. I take my knife, I cut down. What I get out is a square. Okay? So I'm supposed to get some sort of square piece. Okay. If I cut there, if I cut slightly further along, okay, I get, a slightly larger square because that slice down in the R region is slightly larger. And so if I do one more just for effect, if I slice here, get maybe a piece like that. So these are all my slightly weird, slightly funky cross sections. So the solid is sort of coming out of the screen at you, and you have all these nice square cross sections. Okay, maybe that's helpful to think about, maybe it's not. How are we actually going to get into this problem? Well, the key is we need to be able to interpret a definite integral as an accumulation of something. So we can think of a definite integral that we write down here as an accumulation of these cross-sectional areas as I integrate along the x-axis to give me the complete volume. So my two-dimensional cross-sections, the squares, are going to accumulate along the x-axis all my slices to give me the three-dimensional volume that I'm interested in. Even if I can't picture what's going on, this is going to be the correct expression. So conceptually, what we're going to see is, okay, as I integrate horizontally along the x-axis, we're going to get an integral from x equals 1 up to, remember, we figured out that was a 5 there. So those are going to be the limits of my integral. And then I need to figure out what the area of my cross-section is at each point along the x-axis. So I've got this square here, I've got this square, this cross-section at that point on the x-axis, and so on. Okay, I'm going to take the accumulation of those with respect to x as I integrate along. But remember, okay, the rule defining the region R changes, okay, at that intersection point, which remember previously I was calling A, B. So what we're going to really do is split this up into two integrals. So we're going to go from 1 up to, I was calling that A, and we're going to take the area of my cross section. And I'm going to then integrate from A up to 5, and again take the area of the cross section. Now, the really nice thing is these are just squares, cross sections. So if I know the side length of one of those squares, I'll just square it to get the area of the cross section. Okay. So if let me tidy this up a little bit. Nope. Okay. That's a little bit better. Okay. So if I take this point here, and I call that x, what is the side length of that square cross section? Well, it's given by ln x, right? That was the distance from the x-axis up to the curve there. And over here, if this is my point x, that's going to be 5 minus x, because that's the rule giving me the pink curve. So here, I'm going to go 1 up to A, where my area of the left-hand region cross-section is given by ln x all squared dx. And then I'm going to integrate from A up to 5 of 5 minus x all squared dx. Okay. Now, for just concreteness sake, A was kind of a notation that I was using to refer to that point. If we wanted to be super precise and make sure we were definitely going to get our points, I would actually write down the value of A that I figured out in part A. So it was 3.69344, 3.69344. Okay. Notice we didn't really need to use our calculator in this part B. We'd done a lot of the work beforehand. So that is the expression. We're not asked to actually calculate it. We could figure out the numerical approximation of this volume, but we weren't asked for it, so let's not do that work. How were our points divvied up here? Well, we get 2 points for having our integrands correct. So those square cross-sectional areas. And we get 1 point for the overall expression. So the sum of the integrals with my limits of integration being correct, all that good stuff. So 3 points up for grabs here. Okay, final part, part C, before we send this region R off into the sunset to enjoy the rest of its life. So here, we're told that a horizontal line is dividing the region R into two equal areas. So I'm going to sort of kind of guess, eyeball that, so maybe it's around that. Okay, so this is the line y equals k, and this region up above is supposed to equal the area of this region down below. Now they're asking us to write down an equation that we could use to solve for k. They're not asking us to solve for k, they just want us to set up the problem for somebody else to solve, I guess. Okay. So conceptually, we need to think about how can we split up the region R into these two halves using integrals. Well, I'm taking a slice with that horizontal line horizontally, right? So if I want to calculate this area down here cleanly, parallel to that cut line y equals k, I can use horizontal skinny rectangles. And similarly up here, to calculate this area, okay, I can use horizontal skinny rectangles there. There I'm really wanting to think about integrals with respect to y. Think back to part A when I said we were going to have to think about this region R with respect to dy later. Well, we're here. This is now later. Okay. So what we are really saying is when I do one of these integrals, let's say I do this integral to get that area, let's call that area 1. Well, area 1 is supposed to equal 1/2 the area of the whole. So the area of R. Okay, well, let's think about this. So I figured out the area of R earlier, right? You can pull up your calculator. I have it written down here. Okay, the area of R, oh, I don't have it written down here. Wonderful. Let me pull up my calculator. Oops. Okay, what was my area R? It was 2.986. Okay, rounding. So 2.986. That's going to be the right-hand side of my equation. And now for the left-hand side, right, we worked out how to think about this region R as a dy integral. So this time it is, you'll remember, it's the integral with respect to dy of 5 minus y minus e to the y. If you've forgotten how that came up, if you skipped earlier, go back to part A and see how we decompose this region R into skinny horizontal rectangles and how we figured out the length of each of those rectangles using the rules for the two curves involved. But here I'm just kind of pulling that out of our back pocket because we saved it from earlier. Well, what are the limits of my integral? Well, again, you can see my horizontal rectangles are starting down at y equals 0, and they are continuing up until I get to that dividing line at y equals k. Okay. I stop there because that is my half of the region, calculated the area of it. So 0 up to k, the integral with respect to y is supposed to equal 1/2 times 2.986. I could divide that by 2 if I want to, but it's perfectly acceptable as it is. We are done. So let's see, how were the points divvied up here? We get 1 point for our integrand. Okay, so this 3-term y variable expression. We get 1 point for our limits, 0 and k. And we get 1 point for the overall equation. Now, you could have alternatively uh, found out the region up above. That would be perfectly acceptable as well. Your limits would be slightly different. You still get correct full credit. And that is it. We are done with the calculator section of the free response questions. If you've been doing these in order, congrats. I'm going to say goodbye to your calculator for better or for worse. And now try the FRQs that are calculator not allowed. This was a lot of conceptual area, volume, definite integral accumulation stuff. If you're comfortable with that, it might have gone really smoothly. If you're not, maybe rewatch, maybe look out for some similar problems in future. Part B in particular, with that hard to conceptualize three-dimensional figure, was kind of tricky. It was really testing, are you comfortable working with this idea of accumulation without really being able to see the object directly? So let me know how you got on with part B, because I think that was probably the trickiest part of this FRQ. If you want to see me run through the remaining FRQs from the 2012 paper, I'll put a link to my complete playlist right here. If you want to see the multiple choice question run-throughs from that same 2012 paper, I will put a link here. And apart from that, I will just look forward to seeing you very soon. Bye.